because what the task is going to be is you're going to be given two sets of three spectra, the infrared, the NMR, and the mass spectra, because those are the three types of spectra you need to learn to analyze. And then you work out what the molecule is based on the three spectra. So we're going to have a lesson sort of looking at infrared, what information can you get from infrared, then one on NMR, one on mass spec, and then how you can tie it together. So let's have a look. And first of all, if you look at the booklet, there's a FET simulation in there, and it sort of just shows you different frequencies of light, whether it's microwave or infrared or so on, will affect molecules in different ways. Now, IR affects most molecules, not all molecules, but it affects most molecules by giving them energy so the bonds stretch and come closer together. So it's you get what we call IR stretches, and where they stretch symmetrically, so both hydrogens move away equally and come back, or it could be asymmetric, so the way the energy is being transferred, that's the one bond gets longer and the other one gets shorter, or the bond's angle can get smaller and bigger. Okay, that's a bend. And then there's also the various twists that it can do. Now, you don't have to know all those various things, just know in the background that you do have different ways that infrared is absorbed, because you'll be getting different signals in the IR spectra according to whether it's what they call a wag, one of these is a wag and so on, or whether it's a stretch. Okay, so there we got vibrate, stretch and bend. So that is what an infrared spectra looks like. So you've got the wave number, which is the inverse of the wavelength. Wavelength is in centimeters, so the inverse is 1 over. So in other words, the bigger the wavelength, so the longer the wavelength, what can you tell me about the wave number? Is it the smaller the wave number or the bigger the wave number? If you think of 1 over centimeters, so yep, correct. So if you have a wavelength that's 1 centimeter long and another one that's 10 centimeter long, I think you can see that 1 over 1 is bigger than 1 over 10. So the bigger the wavelength, it normally means it's got less energy, so the smaller the wave number. So the wave numbers over here have got less energy, and as you go over, it's got more energy. So the bigger the wave number, the more energy in the infrared signal that comes through. Then you can measure how much the infrared has been absorbed, or you can measure the amount of infrared that has gone through the sample, that's been transmitted. So what you can see with this, and you'll only get the transmission. I'm only mentioning that you can get absorption, because if you say carry on with chemistry, you do this again in first year and you may be given absorption spectra. They're just simply the opposite. So if you've got a big peak where it's being transmitted, then this goes from 0 to 100, so there's not very much being transmitted through here, so that'll also be like a big absorption peak if we did the reverse. Okay, right, so that's the general thing. Now, a thing you also have to work out for with infrared spectra is the scale down at the bottom. Notice if we go over here, it's 500, 1000, 1500, 2000. Can you see the scale is the same? But then you would expect this to now be, 2500, and it's 3000. So a lot of spectra, infrared spectra, show a scale change after 2000. It's just because this section tends to be spread out a bit more, and so the peaks get sort of broader and it gets a bit mucky, so they've just condensed it a bit. Not every IR spectra is like that. So have a look. Now, the ones you will be getting in the assessment task and in the teacher marked assignment are all this way. So in other words, they'll all have a change at 2000. But if you were going and practicing on elsewhere, so you found a site that gave great examples, just have a quick check to see if the scale changes here or if it's the same. Because if the scale doesn't change, then your reading will be different. So why does the scale... Yeah, actually good question, April, because I suppose you sort of think that we're reading from left to right normally. I suppose in a way it's because this is going to be the smaller the number, the longer the wavelength. Actually, yes, because normally when we do the electromagnetic spectrum, the wavelength increases that way as well. It's just the way it's done. I don't think there's any particular reason why, or I don't know. Okay, so it's always smaller waves number this side, larger wave number that side. Right, so just the strong peaks mean that the frequencies are strongly absorbed. Okay, so it takes up a lot of infrared light, and there as well, but this area you can see not much has been absorbed, just about everything has been transmitted. We've got like 90% transmission over here. Okay, then we've got some peaks over there. Right, and then I pointed out about the scale and just the units. So for excellence, just like you've done all along, when you give a number, always give the unit if one is applicable. Okay, so if you're saying, I've got this peak at 1500 centimeters to the -1, or I've got this peak at round about 2900 centimeters to the -1. So just be aware of the unit. Then there's an area which we call the fingerprint region. This is where there's a lot of carbon wags and vibrations and so on. So it's very difficult to pick out individual peaks. Now it's very useful, just like you've got your fingerprints, and if you've been caught by the police or something and your fingerprints match and they can identify you, it is an identifier for chemicals. So if, say for instance, they were checking your urine or something like that, and you came up with a particular pattern for a particular drug or something, then if it matched, they know that you had that chemical in your body. So this is the area where the computer will match. Now, you don't have a computer with a great big database of all the chemicals, so you are going to be looking mainly in this area. Hi, Johnny. Okay, right. So what does the IR tell you? It really tells you the functional groups. It's really good for this. And if you know the functional groups, it can tell you what elements are present or absent as well. So these are the ones that are very easy to spot with an infrared. And OH has got a very distinctive pattern. So has an amine, so NH2 and NHR. Both of them are very easy to spot. In other words, a primary or secondary amine. A carboxylic acid is very easy to spot. So is the carbonyl peak. Now the carbonyl peak can appear in what functional groups? Because you've got it in quite a few. Ketone, correct. And there's quite a few. Aldehyde. Not an alcohol, but it isn't in an ester. An alcohol is just simply COH. It doesn't have a C double bond O on it. So it's anything that has a C double bond O. Yep, a carboxylic acid. So does that make sense, Esther? So C double bond O would be in, so as we pointed out, carboxylic acid, ester, aldehyde, ketone, also in an amide as well as in an acyl chloride. Correct, April. Okay, and so there we have them. You know these different ones, as well as a a chloride, a CCl, this comes up in the sort of fingerprint area, so you would never look at the IR first and say, yep, I've got a chloride, there it is, because it's in that mucky area. You'd have to first get evidence from the other spectra that says there should be a chloride and say, ah, yes, I've got lots of peaks in that area, so it's likely to be a chloride. Okay. So then if you know this, you can work out if I've got an alcohol present, I'll obviously have oxygen present. If I have an amine or an amide, then I obviously have nitrogen present. So the IR can also tell you that. Okay. Now, it's helpful to have an idea of more or less where things are. You are given a data table. Okay, so you are not expected to remember everything off by heart. It's really, you're going to be given the 3 spectra, you look at all the data tables, and you match the peaks, and you write on the spectra to say what it is. Okay, so what we've got here is pretty much your heavy atoms are down here, your light atoms are up here. So CH, NH, OH. H is the light atom. Here you'd get like your CC, your CO, your CN, your CX, and the heavier it is, the further down field it is, the further down it is. Okay? But remembering that energy also increases as we go from right to left, okay? It's much harder to pull apart a double bond than a single bond, to make it stretch and come back. Think of a bond like being a spring. If you've got a strong spring, you need more energy to pull it apart and bring it back. So your triple bonds tend to be higher up, and then your double bonds at a lower energy, and then you've got your single bonds. Okay, and this is the main area where you look at. This is only if you've got evidence from elsewhere, and then you've got to, you can say, yes, I think I've got a chloride and I've got a peak in this chloride. Okay, so we'll look at all the different peaks, but this would be an example of a C double bond C peak. Okay. The C double bond O peak looks actually fairly different, and it's normally slightly higher up than this one over here. So we call this a thin medium peak. This one we call, what sort of shape is this sort of peak? Think of your maths. A parabola, yep. So an OH, because it does hydrogen bonding, if you had that's the other thing I should actually tell you, just for background. IR, you can either do it as a thin oil, or mixed with something like potassium bromide or something like that, so it's done as a solid or as an oil, or it can be done in a solution. So if you've got it done in an oil or as a solid, there is lots of hydrogen bonding, and that makes things very broad. If you have it in a solution, then the hydrogen bonding decreases, so it's very distinct little peaks. Now, you will only be given the oil version, so you don't have to sort of, if you see just a tiny little peak over here, I don't expect you to recognize it as an OH, because any OH that you are given, you should always expect to see some sort of parabola type shape. So we know that this compound has some sort of OH in it. We also know it's got a C double bond C in it, and we also know that one of those carbons of the double bond has got a hydrogen attached to it. So there's a hydrogen attached to at least one of those double bonded carbons. Now, if you're feeling blank and saying, how do you know that? Don't worry. As I say, you get given the table, and you would be looking at the peaks down here, and then you would look at your table to see what would correspond. I just know it off by heart because I've done it for a number of years now. So okay, so the lower the mass, the higher the wave number. So we always have those high up there, and we also have, as I say, the triple bonds further to a higher number, then the double bonds, and then the single bonds. Okay, and that point over there, the 3000 point, is the place to start when you want to analyze. So, because you can just look at a spectra and say what's there and what's not there, but you can sometimes miss things. So the way I wrote the booklet and the way I'm going to do it here is follow a pattern, and then that way you won't miss any detail. So the first thing you look at is you look for the 3000 mark, because just below the 3000, round about 2900, because if you think that's 2000, that'll be 2500, 600, 700, 800, 900. So round about 2900, you're going to get all your CH peaks. So that'll tell you there's alkyl, CH3, methyl, ethyl, those sort of groups in there. You should always see some sort of alkyl, because all your molecules are going to have some sort of CH in there somewhere. Okay, so you always look at that first. And that's just to show you look down to around about 2900. So that's the first region. Then you look slightly up in the other direction to around about 3100. And that's the peak that tells you whether you've got a hydrogen, because remember that area is always hydrogen attached to something. So that's whether you've got a hydrogen attached to a carbon double bond. Okay, this is hydrogen attached to carbons that have single bonds. This is a hydrogen attached to a carbon of a double bond. You can see the same sort of pattern, single, double, triple, so that one's slightly more at a higher number. So that will tell you whether you have that or not. It's just as important to say what is not there as what is there. Then you look in this region, and that'll tell you whether you have an OH or NH, because the CH is over here that we've done there. So it'll tell you whether you've got an alcohol, an amine, an amide, or a carboxylic acid, because all of those would have either an OH or an NH. Is that clear? Does that make sense? That you're going to have an NH bond in an amine as well as an amide, and you will have an OH bond in a carboxylic acid as well as an alcohol. So this will be the area that will tell you whether you've got that. So if the line is flat, then you know you don't have an amine, amide, alcohol, carboxylic acid. Okay, correct. So as I say, it's just as important to say what's not there as what is there. Then you'd look further down to this area. You won't be getting triple bonds because it's not in your curriculum. Okay, so you look down here, and as I say, you've got these two different types. You've got the thin, narrow, sort of medium strength C double bond C, or you've got a much stronger, fatter C double bond O. So those are the two peaks you look for. And if you see a C double bond O, then you must think, okay, it can be an aldehyde ketone, ester, carboxylic acid, and so on. So you just check to see what else is there to find out what we have or haven't got. So here's an example of pentane. So pentane has only got carbon and hydrogen. So we don't expect to see anything down here, and we don't expect to see anything over here in terms of the double bonds. Okay, so following our pattern, remember, go on the 3000, look just a little bit downfield. Downfield is what you use with NMR spectra. You just look a little bit down to 2900 centimeters to the -1, and you can say, I've got alkyl, I've got CHs. And as I say, you're always going to have that. But mention that. Say that you have got a 2900, you've got CH peaks, so there will be alkyl groups. Okay, because you can link them with your NMR and so on later. So I've got that. Then we look slightly more and we go, right, I've got no peaks there. So there's no alkene present. Point that out. Then I look further up and there's nothing there, so I don't have an alcohol, an amide, a carboxylic acid, or an amine. Okay, and then the last area I look at, so April, how many? No, you can't say that. That's when you have to go to your other spectra. All you know is that you've got CH bonds, but you don't know if it's 1 or 10,000. Okay, it's obviously, you know, the stronger, or actually no, you can't even say that. So you just know you've got CH bonds. That's all that you know. Okay. And CH bonds where the C is singly bonded to other carbons. So not the CH of a double bond. Right, then the last area you look over there, nothing there, so you know you don't have an alkene or a carbonyl. So you don't have an aldehyde, ketone, ester, carboxylic acid, acyl chloride, and all that sort of stuff. And we also know we don't have an acyl chloride because there's no sort of peaks for chloride down here. Because remember, chlorine and bromine are heavier. And remember, we said the lighter atoms on this side, the heavier atoms are on the other side. So we expect to see more and more peaks for the heavier ones down there. Right. Okay, so here's now where we've got an alkene. So, you know, you obviously won't be told it's an alkene. So you will just be given the spectra and you've got to work it out. But if you just have a look, then you hone in on the 3000, you say, yep, I've got alkyl groups, okay, at 2,900 centimeters to the minus 1. And you look just to the other side, and yes, not only do I know I've got a carbon-carbon double bond, but I know that one of those carbons has got a hydrogen on it. Okay, and it may be even both those carbons have a hydrogen on it. You can't, that's you, as April, you know, was asking earlier, you can't say how many. All you can say is what is there. So we've got at least one hydrogen attached to a carbon double bond. So it could be C double bond CH2, or it could be CH double bond CH, or it could even be CH2 double bond CH2. But do you get the picture? It won't be Cr2 double bond Cr2 because there's no hydrogen then there. Okay, by R I mean a methyl group or an ethyl group or something like that. So that's empty, so no alcohols, amides, amines, and so on. And here is this thin medium strength bond at round about, it's sort of around about 1640 or so. It's normally, the alkene peak is slightly lower than the CO peak that comes higher up. So if you're looking for it, this one's normally slightly lower. It may overlap with an amide carbonyl peak, but otherwise it's just lower. Right, so here's now an example. I'm perhaps going quite quickly. Are you okay with any questions? You getting what I'm saying? Yep, okay. So here we've got an alcohol, and the way you know it's an alcohol is the same thing. You go into the 3000 and then you have a look. Right, I've got my alkyl peaks. I don't have a CH where the C is double bonded, so I don't have an alkene that has a CH on it. Okay, you can't actually, if there's nothing there, you can't say there is no alkene, because it may be Cr2, Cr double bond to Cr2, but you certainly know there's no double bond CH. Then the next area you look is over here. Now this is where you get your OH or your NH. Now the OH peak is very distinctive. It's this parabola. So if you see a parabola, then you think OH. And it's always centered around about the 3,400 or 3,300 centimeters to the minus 1. you'll see that when we do carboxylic acids. Okay, so it's always that broad parabola, and it's because of that hydrogen bonding that it's so broad. And we can't see if there's any NH because they could be hidden underneath. And we know it's actually not a carboxylic acid, and when we do the carboxylic acid, you'll see why. And then we look over here, and now we know that there's no C double bond O or C double bond C. So we know it's not a ketone, aldehyde, carboxylic acid, all those sort of things. Okay, so that's what an alcohol looks like. Notice we've got bonds over here. It's normally this one would be your CO bond. Your CO bond goes to round about 1,000, 1,200. In fact, the old breathalyzers to check your alcohol content, the police would stop you and give you a breathalyzer. It used to work on dichromate, so your organic chemistry where you looked at oxidizing an alcohol to an aldehyde or a carboxylic acid, and then the dichromate turned green. Do you remember that with organic? Yep. Okay. Those aren't really used so much anymore. Now they use infrared. So the CO peak for ethanol is, I think it's at 1200. So they look for a strong peak over here. So if you get the strong peak over here, and the strength of the peak will tell you the concentration of the substance because it's been calibrated. Okay, you've got to calibrate it to try and get the concentration. So it'll tell you exactly, how much ethanol is in your blood based on how much comes out of your breath, which, triggers how big the peak is over here. So now they all work on infrared. So here's now one where you don't have an OH, but you have an NH. Now, amines can be primary, secondary, and I promise you I won't give you tertiary. Okay, so you don't have to worry about that. So you're going to see a peak here that's either 2 prongs or 1 prong. But notice it's nowhere near a parabola. Okay, NH looks quite small here. It can sometimes be quite big, but even if it was a single peak, it wouldn't look like a parabola. Okay, so this is an amine, and you look over here. I've got alcohol. I don't have a C double bond CH, but I have a twin peak, so I know I have an NH2 and not an NH. NHR. It is an NH2. It'll be a primary amine. Okay, I see April's typing there, but I'll answer it when it comes up. And then you look in this area. Yeah, so one peak would be NH. Now, N, of course, has to have 3 bonds. So N will be bonded to 1 hydrogen and 2 carbons. It'll be a secondary amine if you only saw 1 peak over there. And it's normally like a little triangle. It's not a parabola. We will see some. Okay. Right. Now, sometimes you see something over here, and it's because there are sort of NH bends. Remember I talked about stretches, and you can get bends, and you can get wags, and you can get all sorts of things. So we're dealing mainly with the stretches to give our general layout, but this, you may get something like here. It'll never be a nice long peak like your C double bond C or the C double bond O, but you may get a sort of something in that area, and that's because you do get the NH bends in that area. Okay, so here's an example of a secondary amine. So do you see it's not a parabola? See, it may be bigger, but it'll still not be a parabola. So you should always be able to distinguish it between an OH and an NH. Okay, so but the same thing, look at there, go to the right. I've got alkyls, I've got CH3s or CH somewhere along the line. I don't have a C double bond attached to a hydrogen. I have a little triangular, well, it doesn't have to be necessarily little, but it's a single triangular peak that's based in a similar area to the alcohols, around about 3,300. Okay, and that means I've got a secondary amine present. So when you draw possible isomers, you would only draw secondary amines. You wouldn't draw primary amines. Or you could draw a primary amine and say, it's not this because of the IR spectra telling me quite clearly it's a secondary amine. Okay, so when you give your discussion, you're going to be explaining how you got to your final molecule. And we grade you on your discussion and not necessarily so much on your final molecule. So how you used all the information to get there. So you should be able to say, not only is this an amine, it's a secondary amine because I've got a single peak there. Okay, and that's empty, so I know it's not an amide because or it's not an aldehyde together with a NH2 group on it or something like that. Okay, now this is the carboxylic acid, and notice that I seem to have like one single peak, but with a carboxylic acid, because there's actually more hydrogen bonding on it, it tends to broaden very much. So if you remember, the amine peaks in the OH parabola sort of was round about 3,300 to 3,500, round about 3,400 more or less. Okay, the carboxylic acid triangle, okay, centers more or less around your alkyl, your 3,000 roundabout over the area. So just look where sort of the peak or the apex of that triangle is. If it's round about 3,000, you've got a carboxylic acid. If it's round about 3,300 or 400 or 500, then you've got, say, a primary, a secondary amine. Okay, so where exactly it is will help clearly tell you. And also a carboxyl group tends to have a much broader base. I've never seen an amine with such a broad base. You can see it comes from around about 2,500 all the way to past 3,500. This is nearly 4,000. So if you've got that very broad triangle, you've probably got a carboxylic acid. In fact, I would more or less guarantee it. So is that clear on how you would recognize a carboxylic acid? So you just look for that triangle, broad, and it sort of centers on 3,000. So look for the 3,000 mark. You've got CHs, okay? You're not too sure because the carboxyl group can cover everything, but it doesn't look as though I've got any double bond with a carbon attached. And we'll see when we get to this area, we don't. We certainly have this broad triangle, and so that means it's a carboxyl. Now, John says, what if you confuse it by drawing a line and then thinking that they CC bonds? I'm not too sure what you mean there. So I'll let you type it out again. Sorry. So we know we've got a carboxyl, and then if we go over here, now this is, can you see the difference between a CC double bond and a CO double bond? The CC is lower down, and it's thinner. It doesn't sort of get as far down as here. It doesn't absorb as much. It normally finishes around about then. It's much thinner. The C double bond O is quite fat. It's what we call finger-like. It's like a finger sticking down. So you've got the, it doesn't look much different from the ones that don't have anything in the OH or NH area. This comes, if I go back to, can you see, the carboxyl actually had something coming from round about there, going up and then going to there. So the carboxyl group would look something like this, compared to, say, something that doesn't have anything in that area. Do you see that, or am I misreading what you're saying? Okay, John is typing. I'm just going to go very quickly back to where we were, which was the carboxyls there. Okay. Right, and then as I say, that's a finger-like stretch. Now, where that stretch is will also help tell you what type of carboxyl it is. The carboxylic acid and an ester, an aldehyde and ketone, tend to be in a similar area, round about 17, 1720, 1730, at the most 1750. Okay, Johnny, I've got, yep, okay, right. So if you have anything between 17, because there's 15, so that's 16, that's 17, between 17 and sort of 1750, it could be any one of those four. A carboxylic acid, I mean, that tells you it's carboxylic acid. So, I mean, that'll be quite clear. But for an aldehyde, ketone, or an ester, they'll all be in that area. An amide is always lower down. It's always below the 1600. So an amide C double bond O peak may overlap with any carbon-carbon double bond. And an acyl chloride is always high. It's always close to 18, if not over 18. So if you have something like something at 1780 or 1790 or 1810, then centimeters to the -1, then you know you've got an acyl chloride and you don't have anything else. So the position of that carbonyl peak can be very helpful in saying what type of these it is. Okay, so I've got the acyl chloride or amide unlikely, and it's because this peak is round about 1710, so it's too high for an amide and it's too low for an acyl chloride. Right, so here now I've got an amide. So have a look, seeing we were talking about it just now. There's 15, there's 16, there's 17. So can you see it's clearly below 17? So if you see this fat finger sticking down below 17, you know you've got an amide. Okay, but if we follow in our normal pattern, you look for 3000. Now, I do actually have an alkyl group. Doesn't look like much, but you do have peaks round about 2900. So you will have CH bonds because there are peaks there. Okay, they're not perhaps as strong as what you've seen before, but we still have CH. Okay, then I look just on the other side of the 3000 mark, and I don't have a C double bond CH. Okay, so that's not present. And then I look over here. Now, can you see I have got something? So it's either an OH or, you know, those sort of things. Now, it's not a parabola, so it won't be an alcohol. It's not that broad base triangle going all the way from sort of 3600 to 2500. Okay, it's not that broad thing. It's though in the right area of focusing around about 3300, 3400, and I have got two peaks. So is it a primary amide? By that I mean, is it a NH2 group or is it an NHR group on the primary? So I'll have a C double bond O NH2. It won't be a C double bond O NHC something or the other. Say like your amides that you know when you did in organic chemistry the reactions and you made polymers and you did the peptide link. Do you remember the peptide link? Those sort of things would only show one prong because it's not a primary amide. Okay, so we know it's a CONH2, and if we look in this area, it confirms it. We've got a C double bond O, so we know there's oxygen present in the molecule, and we know it is, because it's such a low number, we know it'll be an amide. Okay, so let's flick through it. Esters are the most difficult, I think, to get, so esters, aldehydes, and ketones can be the most confusing when you're looking at an IR, and it's then very useful to check the other spectra, because they will give you, they'll clearly tell you whether it's an aldehyde or a ketone. So if you look at this, my gut feel it's an ester because I have these strong peaks here, but remember what I said, never ever base your initial explanation on the fingerprint area. Only use it after you've worked out what it could be and it supports your molecule. So you've got something here. Well, let's go through the normal pattern. 3000, I certainly have alkyl groups. I don't have the C double bond C with an H on it. I don't have an OH, NH, or anything like that. No alcohol M or carboxylic acids. I do have the strong finger-like peak, so it's definitely a C double bond O and not a C double bond C, because remember the C double bond C is that thin little peak that comes, it's always below 1600. I don't think I've ever seen it above 1600. 1700. It's always below 1700. And so it's in this area where it could be an aldehyde, ketone, ester, or carboxylic acid, but we know it's not a carboxylic acid because there's nothing over there. And as I say, my suspicions would be it's an ester because of these strong peaks, but you would have to look at other spectra to confirm it. Okay, so here's an example of an acyl chloride. So the same sort of thing, look over there, I've got an alkyl group, I don't have a C double bond CH, I don't have an alcohol, carboxylic acid, and so on. Now have a look at where this peak ends. It's 15, 16, 17, it's very close to 18, it's just under 18. So if you've got something in that area, you know you've got an acyl chloride. You won't be given an acyl bromide or anything like that because that's not on the curriculum. And can you see all these big peaks down here? That's from the chlorine. So you can use that as a supporting evidence, but you would use your mass spec when we do that to help support that. Okay, and then as I say, it's not carboxylic acid or amide, and I hope you can work out why you can cancel them out, because there's nothing down here. And we know it's unlikely to be the aldehyde, ester, or ketone because this number is too high, because all the others come round about over here, 1720, and not 1795 or something, what this one is. So do you think you've got the pattern so far? Yeah. Okay. As you work with them, you know you'll be able to just do it in your head. But as I said, but even if you don't, you've got the tables there. So what happens is, what I just simply say in the tables, C double bond O stretch 18, you know, and I give you a range for an amide, or I give you a range for an the ester, and so on. So you get given the functional groups with where the peak ranges are. We just simply don't say strong finger-like. That's what you have to remember. Or broad triangular. That's what you have to remember. Or parabola. But we do give you, you know, that OH would be over here, NH would be over here, and so on. Okay, now what I did in the book, and then I realized after the book was printed, it just looked very messy like this. Yes, Esther, I know, I realized that the reason why in the book I superimposed spectra, because I thought it would make you very much easier to see, you know, when I point out the different positions of the carbonyl peak. But then I realized that it just looks too confusing if it's the first time you've seen the spectra. So what I'm trying to show here is when I and here, so I've overlaid an ester peak. So these are all the CO peaks over here, and those are the chloride peaks over there. So just to give you a feel of, you know, if we superimpose them, what would be the difference? differences. So the one in greenish is actually the ester, the one in black is the acyl chloride. So does that make it easier superimposing them? And when you go and do the booklet and they superimposed, I hope it's now going to make more sense what I was trying to do. Yes, I know. I wasn't allowed to change the book straight away. Okay, so haloalkane, again, haloalkane 3000. We've got an alkyl group. We don't have all the other stuff, nothing over there, so we can cancel out all these functional groups. You must say what's absent and why it's absent. Don't just say, oh, there aren't any peaks, so it's not the ketone, this, and that. Say there aren't any peaks between, 1600 and 1800. Something like that. So just make sure you show to us you have interpreted the spectra. And as expected, you expect to get quite a few strong peaks down over here because we've got a chlorine. But otherwise, there's actually not much to show for it. These peaks over here, as I say, it's a fingerprint. It's all the C, those twists and wags and everything else that it does. Okay, an aldehyde. An aldehyde, it's not always very clear, okay, but that hydrogen that's attached to this carbonyl group, because an aldehyde always has that hydrogen attached to the carbonyl group, that does a sort of particular stretch bend or whatever, and it comes up as a W, but part of the W is hidden under this alkyl group. So if you see a little peak sort of peeking out of the sort of alkyl part there, this bit that's at around 2900, if you see something coming out there, you can use it as supporting evidence. It's not always clear. So if, say, your NMR clearly tells you it is a ketone or aldehyde, and then you see a little peak over here, then you can say, right, NMR told me it was an aldehyde or ketone. This is telling me it's very likely going to be an aldehyde because I've got that little wiggle, little peak over here. Okay. What can be confusing, so I'm just going to step through the, yes, there's something there, no, there's something, no, there's not something there. What can be confusing is this. Aldehydes often have a messy little peak down here. So you can often think, hey, that's a little triangle, that could be an NHR peak, because that's what you'd expect, wouldn't you, if you had a look at that peak? Yeah, because I've told you, if you see a little triangular peak in that area, it often comes higher than, normally your NH is down there rather than there. So again, if you get something like this and you see a peak there and you go, okay, I could have an NH there, and you can write that down, but you need to then look at your other spectra. Your mass spectra will tell you very clearly whether a nitrogen is present or not. So if your mass spectra says there's no nitrogen present, then that can't be an NH peak. Okay. Similarly with the NMR, that's also can be helpful. So in my last lesson, when we tie all these together, then it's so Esther, yep, sometimes you can ignore things because they're small. Sometimes you can just simply get small peaks and they mean something. So for instance, that previous one where I had those CH. April, there's no real thing where it overrides. You've just got to look at all the collective evidence. So if two spectra say one thing and the other one says not, then the two override the one. So that's the way you would go it, rather than saying, oh, IR always wins, or NMR always wins, or something like that. So you have to look at all of them. I've tried to not choose particularly difficult ones, okay, because we're not trying to trip you up or anything. It's only your first time you're coming across spectroscopy, but it's sort of good to know those sort of things. Yeah. Yes, Esther, but sometimes you can get amine peaks that are quite small. Okay, so there we've got so we've got some sort of triangular peak. It is actually slightly higher than 3,500. And so I put this in green. So if you've got something where you query and you think, that could be something, what I've got in green means go and check the other spectra to see for supporting. And then we definitely have got a strong finger-like peak, and we know it's not an acyl chloride, and we know it's not an amide, because remember the acyl chloride is up here and the amide is over there. So it could be ester, ketone, or aldehyde. It's unlikely to be an ester because we don't really have many strong peaks here. And it's likely to be an aldehyde because of this W. But again, do you notice my terminology? I say it's likely. You can't confirm absolutely. Although that's quite clear, but sometimes you get other things. Okay, so this is now the ketone. So ketone, you know, that's why I say this fingerprint you can't really use very properly because you could be going, oh, is this an ester? So do you see how close esters are to aldehydes and ketones? It's you do need to look at other places. So alkyl group, not a C double bond. We've also got a bit of stuff over there, but pretty much that's we can ignore because that one is really small. And we do have this carbonyl peak here, and it is again round about 1720. So it's too high up for an amide and it's too low for an acyl chloride. So you can spell that out as well. You don't have to, in your discussion, state every single functional group that it is not in detail. But you do need to at least show that you've eliminated some and why. Okay, so we aren't just looking at what's supporting your molecule, but why you didn't choose something else. Okay, so this is the table that you're going to be getting. So we've got about 5 minutes left, so let's just whiz through these. So can you see, like alkane, there we've given you 2,900 to 2,800. So we give you this. So you just look at the peaks and see which one of these does it match. Okay. But hopefully if you do enough practice, you're going to, and you do this 4 different areas, you'll be able to see it more clearly. So if you have a look at this, what do you think this would be? So looking over here, we've got I didn't mean to do that. Sorry, I clicked there by mistake. But if you look there, I've pretty much got the alkyl peak. I've got no other peaks higher up. I've got a very strong peak where I'm expecting a C double bond O or C double bond C. So you're thinking of hopefully by now aldehyde and ketone. You could be thinking of an alkene, but alkenes normally are not quite as strong coming down. Alkenes normally finish 3/4 of the way. I haven't really seen much where it goes beyond that. We say it's a medium peak compared to the carbonyl, which is always a strong peak. Okay, so it's then. So you just go by process of elimination, and you would go, okay, I don't have any peaks over here, so it's unlikely to be an ester. Because if I look over here, let's remember that ester, aldehyde, or ketone. And so you look for this W. And you've got it, so it's very likely going to be an aldehyde. Do you think you would have come up with an aldehyde? Yep. Okay. Now, in case you're wondering what are these gaps for, sometimes a substance is put into solution, and then the solvent actually has peaks. So this actually is an example where it's been put into solution. So they've removed the solvent peaks because they would have been really, really strong. So they just simply deleted them from the spectra. Who would like to have a go at the second one? So let me click for there. So it's an aldehyde. You may have come up with a ketone, but as I say, that was the defining characteristic. Ester was possible, but there wasn't much over here. And you certainly should have been able to eliminate all of those. Carboxylic acid, great. So can you see that big broad triangle from round about 2,500 to 3,500? So it's nearly covering my alkyl peaks. Right, got that. And of course a carboxylic acid must always come with a carbonyl peak, and that carbonyl peak should be around about 1720 or so, you know, below 1750 to 17, but certainly not below 17 and not by 18. So that is definitely carboxylic acid. What about this one, number 3? Okay, well done. It is an amide. So great. It was a tricky one because my carbonyl peak was a weird peak. It got broadened out rather than the strong finger-like one. But you can see we've got the alkyl, and we don't have any alkene. There is my 2 little peaks. Yes, so well done, Esther. It looked like a parabola, but those prongs showed it wasn't. So an alcohol will always have a clear parabola. So if you go, that looks like a parabola, but not quite, then you know it's not an alcohol. Okay? So we know it's a NH2. And if we look in this area, we can see that there's, remember an amide is low, it's below 17. And if that's the 17, it's below the 17. But I do agree it's a bit of a weird peak. But amide is the one. Okay. Racing through these. So if we have a look, we do have an alkyl. That could be something, or it could just be muck. Okay. So you check your other things. But it's certainly not a parabola. And it's not a peak that you would associate with an amine, you know, with an NH or NH2, because it doesn't really have 2 peaks in it. So you're looking here at pretty much something that has got a C double bond O in it, and probably some CO peaks. So this is probably an ester, because it's round about the 1720 or so. So it's in that area, it's aldehyde, ketone, ester. Yep, it's just those 4. There may be a W hidden in there. It's not that clear. I've got some nice strong peaks there, which makes me lean towards the ester. But this is a case where, you know, sometimes you get given information, but you need to look more for other places. So it was actually a ketone, so I've underlined that. But you could have come up with those. And I put amine in green just in case you going, is that a nitrogen or not? And then you would check. But you could definitely exclude these. Okay, because of the position of that. So you know it's not an amide, and you know it's not an acyl chloride because of that position. And you know you don't have the parabola, and you know you don't have that carboxylic acid. Can you see the nice clear parabola? So you know it's an alcohol. And you also see that little peak there, and there's that other C double bond C peak. So you know it's a molecule that has an OH as well as a double bond in it. So it's a molecule that's both an alkene as well as an alcohol. Over here, again, that W is telling me it's probably an aldehyde, but you look through, don't have any alkenes there. That could be a secondary amine,